So you see my picture now? Is it okay? Okay.
नमस्कार। सत्य प्रकाश गार्गी को हम फॉर्मली वी वेलकम डॉक्टर सत्य प्रकाश गार्गी, बट आई वुड एड्रेस हिम एज सत्य। ये मेरा क्लासमेट था 1966 से 1970 और हॉस्टल नंबर 3 में रहता था और कभी कभी मुझे राजमा चावल खिलाता था और मेरे आलू के पराठे खा जाता था। So that's we had joined geological survey of India together, एक साल आगे पीछे शायद, and Satya Prakash was posted in Jabalpur and he had done in very tough forest areas, and for some time he was the Mineral Exploration Corporation of India, and like all geologists from Punjab Ministry do, he also got transferred to Chandigarh. And after he came to Chandigarh, he got it suddenly. उसके पुराने रिसर्च के जो पैशन थे वो जाग गए और इसने कुछ जुगाड़ करी बड़ी जबरदस्त और he left the job and शायद पता नहीं छुट्टी पे आया हो, पर जीएसआई में सरकारी नौकरी में ऐसे छुट्टी उट्टी नहीं मिलती थी. He came over to Miami University, Oxford, Ohio for a doctorate, and he spent 5 years taking some courses and then completing his doctorate. And uske baad mein he had a life full of variety and struggles across USA, and he had done some very rough and tough field work, especially जो story मैंने अभी जब से मैं आया हूँ हॉपकिंटन में, गार्गी से मेरी तकरीबन हर रोज लंबी बात होती है, और जो अलास्का वाली कहानी इसने मुझे बताई वो कभी हम फिर फील्ड वर्क की गपशप पे बात करेंगे. बहुत ही टफ फील्ड वर्क किए हुए हैं सत्य ने, और अभी जो जिस टॉपिक पे सत्य इज टॉकिंग टुडे, ये इसकी एक ओरिजिनल थिंकिंग है जिसमें पढ़े लिखे जो फिजिक्स वाले हार्डकोर फिजिसिस्ट हैं वो इसको कुछ क्रेजी बोलेंगे, और मैंने भी सुनी और मैं पिछले कई सालों से सत्य की ये बातचीत सुन रहा हूँ, तो मुझे लगा कि एक करेज है सोचने का और फिर कहने का. तो मैंने अभी he had sent a publication to नेचर ने अपने सिस्टर जर्नल में उसको ऑनलाइन पब्लिश किया है. तो मुझे ये सुन के पूरी बातचीत ये लगा कि इट्स टाइम दैट ऑल अदर्स लिसन टू डॉक्टर सत्य प्रकाश गार्गी, एंड वी आर वेरी ओल्ड पीपल. आई एम नियरिंग 73. सत्य बीएससी करके आया था तो थोड़ा सा हमसे भी ज्यादा बुढ़ा है, तो सत्य इज plus 75 but still on the right side of 80, and so over to Dr. Satya Prakash Gargi, the veteran freelance researcher. आज की तारीख में he is doing everything on his own, and जब भी बात करो तो he says अभी मेरे को रिसर्च वर्क करने वाला है और बहुत कुछ पब्लिश करने वाला है. तो hats off to that spirit, a great spirit, a veteran, an old friend. Over to Satya. Come on, Satya. Tell your story.
Thank you, Arun. Thank you very much for this introduction.
Anil Mathur is already there. He's listening to you.
Gargi, I'm here.
Okay.
Nice to see you.
Say again, I couldn't hear that.
Anil,
you're welcome.
दोबारा बोलो जो तुमने बोला था उसको. He wants to hear you.
You are welcome, Anil Mathur.
Oh, great, Anil. Great, thank you. Yeah. Great.
So
okay.
I ensured that I join you on this topic.
Oh, thank you so much. Thank you very much. Thank you. Thank you, Anil. Thank you.
सत्य के पुराने जिनको बोलते हैं वो जिगरी दोस्त नीतीश दत्ता, the retired Director General of Geological Survey of India, is already there. And one by one बहुत सारे और आएंगे. सत्य, you carry on. Don't look at them. नहीं तो talk नहीं हो पाएगी.
Okay, all right. Okay. Thank you.
We
Thank you
remember your
all.
speech.
Thank you for coming to my presentation. Thank you so much. This gives me some encouragement, to write more. Okay. The title of my talk is An Unorthodox View of the Age of the Universe. And this presentation actually is part of my paper titled Measuring the Decay Constant of Rubidium-87. Is the decay in radioisotopes linear? Manifestation and disintegration of the matter in space-time and age of the universe. Okay. This is published in Solid Earth Sciences. It's an open access journal. You can read this article on Google. Just type the few words of my title, Measuring the Decay Constant, and my name, and you will see the title. You can access through the Science Direct or Google Scholar. Okay, now, we know that right now the popular view of the age of the universe is about 14 to 15 billion years old, and that view is based on the receding velocity of stars. So, but as the universe is made of matter, so in fact, the age of the universe should be based on the age of matter. But we cannot determine the age of every kind of matter, but we can certainly determine the age of radioisotopes or unstable isotopes. Okay, we can do this by two ways, either by using the basic radioactivity equation. So in this equation, the decay constant which is used, that is an exponential decay constant. That is the decay constant which is measured in the laboratory. Okay, so exponential decay constant means that is the decay constant is based on the relative amounts of the parent and daughter isotopes. Okay, so as the parent isotopes decay, so this decay constant is actually not constant. It will increase with time. As the parent isotopes decay, their amount becomes smaller and smaller. The decay constant will become larger and larger, and eventually the decay constant of this kind will become infinite. The other method is by assuming that the decay in radioisotopes is linear. That's my view. This is the first time I present that view in this paper, that the decay is not exponential, it's actually linear. So I will talk more about this linear decay. Now let's go to the first method where we use radioactivity equation. This is the basic equation of radioactivity, and it is actually from this equation we derive the equation to measure the age of the rocks. But here I use this equation to determine the time when the parent isotopes were formed in the universe. So now this entity NP is the number of the parent nuclei which exist at the present time. That we know that from meteorites and other theoretical models and all that, we know that. So Ni is the total number of parent nuclei formed in the universe. That's the total number, or you can the total amount of parent isotope formed, either manifested or formed wherever in the interior of stars, whatever. So that is the total number. Okay, and TC, that's what we want to determine. We want to solve this equation for TC. TC is the time of creation of the parent nuclei. Okay. Okay, please excuse me, I had to get a little water. My throat is dry. Just excuse me for a minute, please. Okay. All right. This table shows the time of creation, TC, of various unstable isotopes, assuming exponential decay constant. That means the decay constant which is measured in the laboratory by different methods. There are so many methods by which we measure the decay constant in the laboratory. Okay, this is the example of uranium-238. So this is the present day ratio of the parent isotopes, and this is the present day daughter isotope ratio of this uranium-238. Or so the daughter isotope is lead-206. So this is the ratio of lead-206 lead-206 by lead-204. Okay. Now lambda is, we know the lambda. Lambda is the decay constant. We know the present ratio of the parent isotopes, that is 7.1 something, and Ni is the total number of parent nuclei formed in the universe. We get that by adding these two numbers, because the decay is 1 to 1. One parent isotope decays into one daughter isotope. So if we add these two ratios, we get the total number of isotopes that are formed in the universe. So that's how we get the Ni. So Ni is, by adding these two values, we get this value. And then we solve this equation for TC, and we get a value of about 7.73 billion years. So this uranium-238, according to this equation, was formed in the universe about 7.73 billion years ago. Okay. Now, so like that, I determined the. I'm sorry, I had to go to the slideshow. I'm sorry. Okay. So this is the for uranium-235. Its age comes to only like what, 5.7 billion years. Very short age. Okay, it's only about a billion years longer than the age of the solar system or age of the Earth. Okay, now we'll take another example of. Sorry, where we are going. Okay, this is the example of rubidium-87. Okay, here also we know the present day ratio. This comes from my paper of Gargi 2012, and similarly the present day ratio also comes from the present day daughter isotope ratio, also comes from my paper of Gargi 2012. And I also, it was a theoretical model. In that model, I suggested decay constant to be 1.408. Normally they use 1.42 or something like that. So I suggested that the decay constant should be 1.408 according to my model. So here we calculate the age of the rubidium-87, that comes out to 155 billion years. Okay. But this is the table showing all the ages of the various isotopes that we use in this model, in this theory. Uranium-238, uranium-235, thorium-232, lutetium-176, samarium-147, rubidium-87. Okay. Now, let me go back. There are two theories, one from the astronomers and astrophysics, that the matter is formed in the interior of the stars by nucleosynthesis. That means the heavier atoms are produced from the lighter elements by neutron capture. That means the neutrons are added, or you can say added to the lighter elements, and the heavier atoms are produced. And then there is another theory by particle physicists that's called the unified field theory. According to that theory, progressively heavier elements are formed in space-time. So that in space-time, by time, heavier elements are manifested in space-time. So if we now look at this, now rubidium-87 is lighter than samarium-147. So according to these theories, the age of rubidium-87 should be higher than age of samarium-147, but it's the other way around. Similarly, in this case, uranium-235 being lighter than uranium-238, its age is only 5.7, whereas the age of uranium-235 is 7.7. So that means they violate both these theories. So either probably there is no order between these elements, or there is something wrong between the decay constant that we are using. That's why we are getting these kind of results. So here again, as I mentioned earlier, the time of uranium-238 is much earlier than uranium-235. That means the age of uranium-230 is older than uranium-235, but which it should have been other way around. Similarly, samarium-147 is older than rubidium-87. Okay, and then third thing, we see that the age of uranium-235 is too close to the age of the Earth. And again, I forgot to mention that this equation that I'm using to calculate the age of these radioisotopes, this gives the maximum possible age of that atom. So the assumption is that there were no daughter isotopes formed in the universe at that time, either by manifestation in the space-time or by stellar nucleosynthesis. So in other words, all the daughter isotopes owe their origin only to the decay of parent isotopes. That's the assumption. So if the daughter isotopes are produced, say in the interior of stars, that would again further reduce the age of the uranium-235. It is the maximum age is about 5.5 billion years, and if their daughter isotope lead-207 is also produced in the interior of stars, this age would be even less than that, almost even less than the age of the Earth. It's not possible. So something is wrong. Okay, now the second method, what I call is by assuming that the decay is linear. So we can, by assuming that decay is linear, we can determine the age of any radioisotope, okay, by extrapolating from the present day daughter isotope ratio through its ratio at the time of the formation of the Earth up to we extrapolate back to the x-axis. So when it meets the x-axis, that means at that point, y-intercept is 0. In other words, the daughter isotope was 0 at that time. The daughter isotope ratio was 0 at that point where that line intercepts the x-axis. So what's the meaning of that? The daughter isotope is 0. That means that is the time where its parent isotope came into being. It was manifested, and it started decaying from that point on. So, where that array or the line intercepts the x-axis, so the daughter isotope ratio is null at that point. So that means the parent isotopes start disintegrating from that point on. They start decaying from that point on, and the amount of daughter isotopes goes on increasing with time. Now this is the table to show. These are the XY plots to determine the time, the age of the parent isotopes by extrapolating, or you can say the present day ratio through its ratio at the time of the formation of Earth up to the where it meets the x-axis. Now here in this table, time of manifestation of uranium-238. Okay, so let's go to the again. Okay, here in this case, this is the present time. 00 means this present time. At the present time, the daughter isotope ratio is 16.68. Okay, of what? What are the daughter isotopes of uranium-238? Lead-206 by lead-204. Lead-206, lead-204 ratio is 16.6, because we measure in terms of ratios. We cannot measure the total number of isotopes in the universe, so we measure by ratios. So uranium, lead-207 to lead-204 ratio is 16.6. So at the present time, it's 16.6. That means, and at the time of the age of the time of the formation of the Earth, 4.55 billion years ago, its ratio was 9.37. So with the time, as the more of the parent isotopes decay, this ratio has increased to 16.6. Okay. Now we plot this. Okay. This is the slope. This is the intercept. This is the intercept of this array at the x-axis. So that intercept shows the age of this uranium-238 as like about 1.029 billion years. Sorry, 10 is raised to power 10. So it's about 10 billion years, 10.29 billion years. That's the age of the uranium-238 according to this method. Now, similarly, if we go to now here, 235, according to this method, is about 14 billion years. Whereas by using the earlier method of this decay constant, the earlier method, its age was only about 5 billion years. Now it is about 14.8 billion years, and so on. Similarly, rubidium, the age of the rubidium by this method is 541 billion years. Okay, it's more than the samarium 147. That's what we expect. The age of the samarium 147 is what? 397 billion years, 397.6 billion years. Okay, and rubidium is 541 billion years. Now this is a table showing the ages of all the radioisotopes which were determined by using this method, by using the linear decay. Now you can see that uranium-238, because this is the heaviest, it has the least age, lowest age. Whereas uranium-87 is the lightest of all, it has the highest age. So there is a really nice order in their ages and the atomic mass. This can be shown graphically here. Again, this is a table. Now, so in this, on the x-axis, we plot the time, that's time of manifestation. On the y-axis, we plot the atomic mass. So this is the atomic mass of the various isotopes. 238 is the atomic mass of uranium-238, and so on. And 87 is the atomic mass of uranium-87. And its time of manifestation in space-time is 541 billion years. And the uranium-238 is time of manifestation in the universe is about 10.29 billion years. Now, so when we plot that XY plot, okay, the intercept is at 935.5 billion years. 935.5 billion years. And is the y-intercept, that's the intercept at the y-axis, which shows the atomic mass, is what? 241.65. That is about 242. So the y-intercept is 242, and the x-intercept, that is the 936. So the x-intercept shows the age of the universe. Let me show it now graphically. XY plot. So this is the atomic mass. We plot the atomic mass of the various isotopes, and this is the age of manifestation of these isotopes. Rubidium-87 has the highest age, about 500 something, and the uranium-238 has the least age, about 10. Now this graph intercepts at 936 billion years. So it shows the zero mass. Zero mass means this is the time when the matter appeared in the universe, when the universe originated. So that's the age of the universe, 936 billion years. Okay. Now their correlation is very good. Now let's see. The correlation coefficient is about 0.95. This is a very good correlation coefficient for this relation. Yeah. So this correlation shows a very high degree of correlation, minus 0.9574. Okay, now this array, or this linear array, I call it as cosmochron here. So this line is cosmochron. Its y-intercept is 242, its x-intercept is about 936 billion years. So the x-intercept is at 935.479. That indicates the age of the universe. That's where the universe, the matter manifested in space-time. And the y-intercept is 242. This is what it does. What it shows. 242 is the atomic mass of the heaviest element that could exist today. This graph shows the atomic mass of the heaviest element that exists today, and that's what we find. That's true. That itself is the proof of this theory, because we know 242 is the atomic mass of plutonium. Okay, plutonium occurs only in traces in association with uranium. Most of the plutonium is formed in the nuclear reactors when we use the uranium for the energy. So plutonium does occur only in traces. And that itself is the proof of the theory. You don't have to go outside. In this theory, I have made no assumptions. If I made any assumption, those are by themselves are proved in the theory itself. Now, similarly, just as we calculated or estimated the time of the formation of the various radioisotopes or unstable isotopes, similarly, we can determine the time when they will be completely disintegrated, when they will be completely decayed into their daughter isotopes. Okay, but there is no equation for that. Just like in the earlier case, there is no equation to determine the time of total disintegration of a parent isotope. However, again, assuming the linear decay, we can estimate their time by assuming linear decay. That means we extrapolate the parent isotope ratio at the time of the formation of the Earth. At the time of the formation of the Earth, the ratio of the parent isotope will be more than at the present time. So if we extrapolate from that point on through its ratio at the present time and all the way to x-axis, so where the x-axis, where the array would intercept the x-axis, that would indicate the time of total disintegration of that parent isotope. Okay, so in this way, this is again the table where I have calculated the time of total decay of the various parent isotopes. So here, again, for example, taking this example, on the x-axis, we plot time, years ago. Okay. On the y-axis, we plot the parent isotope ratio. Now, keep in mind here we are using the parent isotopes to determine the age of the to determine the time of their total disintegration. In the earlier, when we calculate the estimate the time of their manifestation, we use the daughter isotope ratios. Here we are using the parent isotope ratios. So because the parent isotope ratios will keep on decreasing with time, so starting from the time their ratio at the time of the formation of the Earth about 4.55 billion years ago to its through its ratio at the present time until it intersects the x-axis, that point will indicate the time when that parent isotope was totally disintegrated into its daughter isotope. So in the case of uranium-238, that time comes to about 14.7 billion years. So in about from now on to about 14.7 billion years, uranium-238 will be completely decayed. Now, similarly, uranium-235 will decay in about 14.88 billion years. Okay. So similarly, I calculate for these other isotopes, thorium-232, lutetium-176, samarium-147, and rubidium-87. The time of decay, total decay for rubidium-87 is only about 68.74 billion years, whereas in case of samarium, it's about 548 billion years. No. Okay, let's go to the table. I think 54.8 or samarium is, okay, this is the time, sorry. For samarium, the time for total decay would be in about 150 billion years, okay? And in the case of rubidium, it will be about 68 billion years. So these are the numbers. Now, if we go look at the table, uranium-238 will decay in about 4.437 billion years. Giga years means billion years. And rubidium-87 will decay in the future in about 68.784 billion years. Samarium-147 will completely decay into daughter isotopes in about 150 billion years. Now, this is the time of disintegration from this present time. Now, we can find the time of their existence, the total time of their existence in the universe. That means from the time they were created to the time they were totally disintegrated. What is that time? That's the time of total existence. So when I calculate that, what we do, we add the time of manifestation with the time of decay, and we get the TE, that is the time of total existence. So in this case, uranium-238, from its time of creation to time of its total disintegration, that period will be 14.73 billion years. In the case of rubidium-87, it will be 610 billion years total, starting from the time of it manifested in the universe to the time it was completely decayed. Is about that time period is about 610 billion years. Now you can see that there is a nice order between their age and their atomic mass. You see that rubidium-87 is the lightest, and the total existence time is 610 billion years, and the uranium-238 being the lightest has the least total existence time of 14.7. We can show this graphically here. This is the table. Same thing. We on the x-axis we plot the time of existence. On the y-axis, we plot the atomic mass. So here, on x-axis, for rubidium-87, the total time of existence is 610, while uranium-238 is only 14.7. And you see, when we plot them on an XY plot, we see a very good correlation. Correlation coefficient is about minus 0.948. It's a very good correlation. Okay, and the x-intercept, where that line or the array would intercept at x-axis, is about 1104 billion years. So what is that? That is the total time of existence of the universe. That means from the time the universe appeared in the space-time to the time it will be completely gone, it will meet its demise. That time interval is 1104 billion years. It's about, you can say 1.1 trillion years. Okay. Now in this graph also, the y-intercept is at 242.43. It's remarkable. In both these graphs, the y-intercept is at 242. Very significant. That itself shows that in future there will be no nuclide with a mass of greater than 242 would ever appear in the universe. No nuclide with a mass of greater than 242 would ever appear in the universe. That's the limit. So that means although we have they have made in the laboratory many heavier isotopes, although they don't occur in the universe, but naturally they will never be produced in the universe. That's what this graph shows. Again, it's remarkable in both the cases, the intercept is at, y-intercept is at 242. Okay. Now, so we can see that the time of the universe would exist, the total time the universe would exist, or the time of demise, is about 1104 billion years. So I mentioned earlier, when we plot the time of existence of the various parent isotopes against their respective atomic mass, we get a good correlation, linear array, which intercepts the x-axis at about 1104 billion years. Okay, and that's the time that indicates the time when all the radioisotopes will totally disintegrate. And we can assume that the other stable isotopes like carbon, hydrogen, oxygen, nitrogen, iron, gold, silver, all those metals would also decay. But there is no proof for that. We just assume. And again, there is a theory from the physicists. They say that all matter would disintegrate in future in about, if I'm not wrong, I don't know exactly, but it's about 100 to 200 billion years. And that time matches with this, because if we subtract the age of the universe, 936, from this total time of existence, 1104, we are left with 168 billion years. So in about 168 billion years from now on, all the matter would disintegrate. Okay, at least the radioisotopes would disintegrate, and we assume that the other stable matter, all the stable elements, all the nuclei would also decay. Now this is the graph showing that. On the x-axis, I plot the time of total existence of the various nuclides, okay, unstable nuclides. On the y-axis is their atomic mass, and they show a very nice correlation. As I showed, that the correlation coefficient is about 0.94, which is very good. Okay, and I named this plot, this array, as dotochrone. That means demise of the universe chron. That gives us the time when the universe will meet its demise, total demise. Okay. significance for the y-intercept. I already mentioned again, in both the graphs, the y-intercept is 242. So in the case of cosmocron, this y-intercept 242 indicates that the space-time for elements heavier than 242 has not arrived. Maybe in future, heavier elements heavier than 242 might appear. Okay, but in the case of Dotuchron, this this intercept 242 suggests that this space-time for heavier elements would never arrive, would never come. So that's the heaviest isotope, the heaviest mass of any element that we would see in the universe. So the similar intercept in both relation again, the similar intercept in both the plots also indicate that there is a genetic relationship between the parent and daughter isotopes. Why? Because in the case of cosmocron, we use the daughter isotopes. In the case of Dotuchron, we use the parent isotopes. So that means there is a genetic relationship between the parent isotopes and the daughter isotopes. So it means their evolution, the evolution of parent isotopes and daughter isotopes is complementary and integral to each other. Okay, so that means one owes existence, the daughter isotopes owe their existence to the parent isotopes. They were not formed by any means, either by nucleosynthesis or manifestation in space-time. They were formed only by the decay of their parent isotopes. So that is the significance of these two similar y-intercepts. So again, if what the astronomers think that all the matter was created in the interior of stars by the process of nucleosynthesis, in that case, these ratios would be random ratios. There would not be any relationship between the parent isotopes and daughter isotopes. Okay, so those should be random ratios. But we have established here that there is a relationship. If there is a relationship between the parent and daughter isotopes, naturally, definitely they cannot be. They were not formed in the interior of the stars by nucleosynthesis, but they manifested in space-time. They were formed, you can say, by the interaction of the subatomic particles. Like, you must have heard of those God particle and all that. So what is that? That gives mass to the particles. So that's how the particles were produced, manifested in space-time. And so this is the strongest evidence against the formation of the elements or the matter by nucleosynthesis in the interior of stars. Now, coming back again to linear decay. How the linear decay is possible? Linear decay means a specific number of nuclides decay every year from the whole universe. That specific number is constant. So every year, same number of parent isotopes decay in the universe for the whole universe. That means all the galaxies and all the stars. There are billions of galaxies, and each galaxy has billions of stars. Okay, and their planetary system and our solar system, our planetary system, our Earth, our rocks. In all those, when these parent isotope decay, the total sum of the parent isotope decay in the universe is constant. So now the question is that how the constant number of decaying particles in the universe as a whole is maintained. Who maintains that constant number? What is the power, the authority behind that? Who controls that? Is there a database of all the particles in the universe? Who maintains that database? Do the particles communicate with each other? How do they decide? which particle to decay. Maybe they communicate. They decide that which particle to decay at a particular time, at a specific time, so that the constant number of particles decaying in the universe is constant. I mean, the matter in the billions of galaxies, hundreds of light years away, thousands of light years away, and our solar system, our planets, our Earth, and the rocks, the total number of decaying particles is constant for the whole universe. Otherwise, this relationship could not have been there. This relationship between the parent-daughter isotope, this cosmochrone and the dotochrone would not have been possible. So this is a philosophical question. So now, in our system, our, you can say, mythology, we know that Akashic records, that everything is recorded in the universe. Probably that proves that there is a record of everything in the universe. Thank you very much.
Great, Satya. We like your spirit, and we are enlightened about your original thinking and your courage to think. And we can also see the resistance of those who may think that they know much more to your thoughts. And Satya has not told the story of his struggles in this, in publishing this. There are people everywhere in scientific field who face resistance from the system to any new ideas. Whether it was plate tectonics or whether it is even the truth and myths about the climate change, everywhere, those who speak out, even what's happening over the Himalayas, the system is denigrating the entire Himalayan ecosystem and destroying the entire Himalayan geoheritage, and nobody is willing to listen. They think होता है, सड़क बनती है, जरूरी है, development चाहिए, वगैरह वगैरह. Leave that aside. I can only say that Satya Prakash Gargis, we salute you. We both classmates, Anil Mathur and I, surely we do it, and all others do it, because this is no easy task. And let me tell the audience that as far as I understand, this is not the basic topic of his PhD. This was, am I right, Satya?
Yes.
Yeah, this is a byproduct of his learning and thinking. And that's what amazes me, because we have known him in MSc doing research on paleontology. And then he was in mineral exploration. Then he came to HP Circle, and suddenly he went for a course, and such a long course, 5 years. So Satya Gargi has been a very daring guy all these years. And as we know, he has a lot to do. And as the English poet said, he has miles to go before he sleeps. So Satya Prakash Gargi needs to live beyond 100 years. Otherwise, he won't be able to complete all that.
Conversation, Satya.
सर मैं बीच में 1 मिनट लूंगा. अभी गार्गी सर को आपकी फोटोज नहीं दिख रही होंगी. 1 मिनट बस. मैं गार्गी सर को आपकी फोटोज नहीं दिख रही होंगी. लेट मी कंप्लीट दैट वन, ताकि वो आपको देख भी पाए जब आप बोल रहे हो. गार्गी सर, आप प्लीज स्टॉप शेयरिंग कर दें और प्रेजेंटेशन बंद कर दें, सो दैट कि आप फोटो देख पाए सभी की जो बोल रहे हैं.
ओके, मैं स्टॉप शेयरिंग. ओके,
हाँ जी, स्टॉप शेयरिंग करके प्रेजेंटेशन आप बंद कर दीजिए.
आप थोड़ा सा उसको टिल्ट करो अपने लैपटॉप को, सो दैट तुम्हारा चेहरा दिख जाए और लोगों को पता लग जाए कि कोई बुजुर्ग आदमी बोल रहा है. यार अभी
तो आपको आपकी स्क्रीन पे अब सबकी फोटोज दिख रही हैं?
हाँ
जी. अब आप सर प्लीज, माथुर साहब कुछ कह रहे थे.
हाँ जी.
हाँ अनिल बोलो.
आपको आवाज़ सुन रहे हैं?
अनिल Unmute.
Yeah, it was so nice to hear you and see you after very long time. And excellent lecture, excellent views that we must listen to people. There are always new views coming up in the universe, and yours one is very interesting.
Thank you so much. Thank you. And by the way, let me tell you, Arun mentioned about my struggle. My first paper was rejected by 11 journals.
Yeah.
And it took me
You are not the only one who was rejected.
And this one also was rejected by like 5-6 journals.
Yeah.
So ultimately I got it published. So that's the struggle.
That should encourage you. That should encourage you.
Yes.
होता है. But and let me also tell the audience and especially the youngsters, because this talk is going to be live on Facebook link of our great stalwart Arun Bansal, and also he'll be giving it to me for uploading it on the YouTube Earth Talks. Generations can see this. My idea was getting Satya to speak here was to preserve it and to conserve it for posterity to see, so that a judgment is passed later. Left to myself, I would, for the sheer courage and daring to think originally, I would give the highest award, which I would. And our heart says that Satya Prakash Gargi ji, tusi great ho.
Thank you, Arun. Thank you.
Hello, mutual appreciation.
Thank you so much.
Mutual appreciation.
Thank you so much. And congratulations to you that you retired as DG. That was still an achievement. I was so happy to know that.
Yeah.
Nitish Datta.
Satya we know from 1970.
Yeah, they had started career together in Geological Survey. They were together.
Yes. What did you say, Nitish?
Nitish, तुम कुछ बोल रहे थे ना? बोलो.
You said something?
सुना नहीं. Anyway, now.
No. Well,
he's speaking. Yeah, Nitish.
I mean, Arun mentioned all those struggles, you know.
Can you hear me?
Nitish is
forward.
Can you hear me?
Yes, I can hear you.
Can you hear me?
Yes.
Okay, because I am on some gadget. Satya, I know you, yeah. Told us a Gita that universe is very big.
Yeah.
It's a repeat of Gita. So, Arun, thank you so much.
Yeah.
All those who know Satya Gargi.
Thank you so much.
All those 50 years or so, 52 years.
See
52 years we know him. Geologists live very long.
Yeah.
So we.
Dr. Gargi, there is a message for you. Dr. Gargi, there is. Right, sir. There is a message for you from Mr. Devesh Garg. He writes that I am 14 years old and it is a great honor for me to listen to the lecture of the great. So, since he has written that one, it was my duty to convey it to you that this is how you have got the compliment from Devesh Garg.
Oh, great. Thank you.
So, Arun,
and let me mention you one thing. This is not a complete story. I still have to write 2 more papers related to this age of the universe.
So,
and one may be a short paper, short communication, and other one will be a normal paper. And then I intend to write a book. I don't know if I will live that long, but that's my intention. That's my desire. That one day I will write a book on this age of the universe.
Ignited young minds. You have ignited young minds.
So let's conclude. Satya Prakash Gargi, take care of your health and.
100 years में हो जाएगा सत्या. Arun ji said you will live 100 years. अभी तो बहुत दिन है. Yeah. Take care. See you next. मेरे साथ अरुणदीप के साथ.
Please let me know if you have any question.
interaction can go on. Interaction can go on the Facebook Live page because people will see it later. And Satya, you will join that group, Social Substance, and you will also keep a watch on the YouTube channel, Earth Talks. Your talk will be there, and it'll be seen by people and commented on by people. Keep it up. Great spirit. We all our compliments to you. We pray for your long life and good health. God bless. God bless.
Thank you so much. Okay.
Arun, I think we can close now.
Yeah.
Thank you. Thank you.
Okay, Arun.
Okay. All right. Thank you.
Thank you, Arun.
Hello, Nitish. What about our other friends from Jabalpur?
Jarur. It's a revolutionary